Hi. Okay, so I'm here today as, I forgot your name, Martin noticed. I'm here today to talk about how we integrate QKD into our product to enable users to encrypt their calls using QKD-generated keys. I've been working at Dencrypt for 7 years, most of the time as a software developer. And when you do a lot of stuff with crypto, in the end, your boss will tell you, now you are the chief cryptologist of the company. So, yeah. The agenda for today is first a company and product presentation, so you get to know who Dencrypt is. I assume many of you don't know. And then I'm going to introduce the CyberQ project, which this whole integration effort is a part of. So Dencrypt was founded back in 2014 by a businessman and a well-renowned cryptographer called Lars Knudsen, who did a lot of research in symmetric crypto. And one of the issues they wanted to tackle was, right around that time, there was a security incident in Norway around the government offices where there was this rogue telecom network set up by perhaps an enemy state. And what they were able to do was to intercept the traffic going from the cell phones to the towers, to the cell towers. So the company was founded to bring strong encryption for securing calls. Lars invented this notion of a dynamic encryption. And the idea, I won't go into details, but the idea is that you take a strong symmetric cipher, and then you wrap it in a changing layer, which gives you a dynamic algorithm for encrypting the text, the ciphertext. The idea here is really to have this moving target defense, and this is one of the key features that we use in our encryption in our products. Today, we are 25 employees based in Aalborg and Copenhagen in Denmark. So the Dencrypt communication solution today consists of end-to-end encrypted communications between government and military functions. We support instant messaging and audio and video calls. We support Android and iOS, macOS, Windows. So we deliver an app for various platforms together with a server system. We also offer interoperability to other communication solutions, such as PEXIP, a conferencing solution. And then all of this is produced in a product where we have a central closed ecosystem, which will hinder, for example, attacks or incidents as the signal gate, where people from outside get into a group chat which contains classified information. And we can deliver this system with common criteria certification, which means that it is possible to exchange restricted confidential information over the system in Denmark and other countries as well. So if we look on the technology side of our solution, what the security features of our system is basically some web server traffic, where we have security through HTTPS. It's instant messaging, where security end-to-end encryption is achieved by doing X3DH and double ratchet, which is the same as Signal does. And then for audio and video calls, we use something called SRTP to encrypt the RTP streams, which is the call data. And in order to set up an SRTP stream, you need a key, and you can get that from different technologies. We use DTLS SRTP to get the key for the solution. And we've been on a journey where we wanted to post-quantum secure our solution, and we've been looking very much into OpenSSL in order to achieve this. So right now we have achieved it for the HTTPS traffic through TLS 1.3, and we're looking to secure our DTLS traffic as well through DTLS 1.3. And DTLS 1.3 is also a major part of this project that we've set off to do now. So we were contacted back in 2024, last year, from some researchers at DTU. And they were interested in doing a project which should advance the use of QKD. They went to us, and they've always had a dream to kind of build these secure video calls, because it's a high priority to them. And here we had funding from something called Innovation Fund Denmark to do this project. It consists of multiple work packages. Secure video call is just one of those work packages. But all in all, it's about advancing the state of QKD and its applicability to the industry. So encrypted video calls is all in all achieved through these layers. I'm going to go into the different aspects of it and kind of build from the bottom up to the encrypted video call stream. First, I'm going to explain how QKD works, or at least try to explain. So I'm not a physicist, but the mental picture you need in order to understand why QKD is secure is QKD in itself is actually just transmitting binary data from a sender to a receiver through plain text. The bits are encoded as photons, and photons, they have a polarization, which means how the wave goes through air, and they have a spin, and you use this to encode the bits to a photon. But it has a particular property, and that is you cannot copy the state of a photon, which means when you have a sender and a receiver, you can read the state once if you know the correct polarization of the photon that was sent. But in a QKD system, Alice and Bob independently chooses which polarized state to send a photon and receive a photon. And what you end up with is Alice encodes some bits, and Bob is able to decode those bits. But what happens is, it introduces some errors, and that's all right. These errors are introduced because Bob has chosen the wrong polarization to decode the bits. So what happens after they've sent all these bits is they tell each other over a classic authenticated channel, I sent with these polarized states, and I received with these polarized states, and now they know which bytes they kind of agree on, and these are the ones that are used as the QKD key output. The reason why an attacker cannot sit in the middle is because actually what happens here is that Bob is able to decode some of the bits for which he did not choose the correct polarization state. So the way to picture it is if you send with one polarization state, if the receiver has chosen an incorrect base to receive in, he has a probability to be able to decode the bit, and he cannot detect if it's in the wrong polarized state. So an attacker would be able to sit in the middle, but because she is not able to clone the photon states, when she is sending the photons, the newly encoded photons to Bob, she will introduce error because of this probabilistic mechanism, and that's how security is achieved through QKD. So on top of QKD, this endless stream of secure bits sits what's called a quantum key management and exchange unit. So we went to DTU and had a look at their setup, and this is a picture from back then. And what you see here is QKDs that are coupled with a QKME, and what they do all day is just transfer secure bits to each other and storing them on a hard drive. Now the QKME, they offer a simple REST interface to be able to fetch the keys. And you can hook a QKME up to different QKMEs, so you kind of, it's not a 1-1 mapping. You can have multi-party communication. So the idea is to be able to get the same key on both sides of the encrypted, or on both sides, the server and the client needs to exchange what's called a key ID, and the key ID that there are different properties denoted by the key ID, the key size, and all that. So the master will get a key by using the target QKME ID, and then he is able to send a key ID to the other QKME, and now both sides have the same key. And this is what we've been trying to integrate into DTLS through OpenSSL providers. So it looks kind of like this. And as you can see, our idea is to model this as a KEM to be able to use the existing provider structures. So really, the key exchange step will contain sending a client ID to the server, and then the server responds with a key ID and its own server ID. And this, and this allows the client to pick up the same key, which we hope will work quite fine. So one of the things we haven't really uncovered yet, this is a research project that is ongoing, and we haven't really gotten that far with it. But some of the things that we are checking for is how performance is implicated by doing RESTful API service fetching while doing a TLS handshake. And then we might also run into some issues around the setup of the QKME and how we do that in a provider context. But yeah, that's more or less what I've had to say about this project. So, are there any questions?
So I'm just trying to understand. You said you modeled this as a KEM.
Yeah.
Through the so you've got a custom provider, and it's your own. You've just invented a KEM basically, which is and you just create a capability within the provider to publish the KEM. Is that the way it works?
Exactly. Exactly. Yeah.
Okay. Right. Okay. So this isn't something that could be rolled out. It's completely proprietary, basically.
It's very proprietary, and it really is a technology review kind of state. For an application to use this service, it has to be connected to these QKMEs, and right now we only have access to them on campus. So what we do is actually we use a mocked version of a QKME locally to test it out. But yeah, to answer your question, this is really research and trying to see what limits are there to the solution. Yeah.
Okay, thanks. I have a follow-on question, if I'm allowed. You didn't really mention DTLS 1.3.
No.
I would love to hear how you're planning to use DTLS 1.3 in this.
Yeah, so
solution.
Of course, being able to use providers, we need DTLS 1.3. The state of the feature branch right now is in a state where we can actually use the providers. So locally, we believe that it's possible to do this inter-op test. And I'm a bit unsure what will happen when we try it on a real system. But that's research. So then we know the state of it. But I think we're a year out. Like we're a year from the end date of this project.
But you're actually using the feature branch now in your sort of tests and so on?
Right now we're just developing the provider
Okay.
and taking it from there. Yeah.
Cool. Thank you.
Any more questions? Everything you wanted to know about QKD and never dared to ask. That's your chance.
Does this QKD work if you don't have a continuous fiber between the communication partners?
I think you can do it also via satellite, but I'm actually not an expert in that. Yeah.
Okay, thanks.
Yeah.
There's one in the front.
Thank you. For the QKD, you also need a classical authenticated channel, right?
Yeah.
So how to handle that? So
Yeah.
you establish like another connection for QKD and then put it inside TLS.
Luckily to us, it happens through the QKME. It sets up the authenticated channels, and that's set up already. So when we integrate with the QKME, all that is handled by the system itself. Yeah.
If I may, a follow-up question. If you can go back a couple of charts. One more. Here, down here. Yes. So you kind of distribute here the key material, and on the previous chart we did see some HTTPS. So how is this channel secured? I mean, you have the key down here.
Yeah.
You have the up here, you have to bring it down. How is that general setup?
Exactly. So that's through HTTP or HTTPS. So it's just a REST API that you call like this.
So it's TLS underneath.
Yes.
Yes. Hopefully.
So if someone listens in on that connection, you need to be very certain that they don't. Yeah.
Okay, I understand. Any more questions? We still have 7 minutes left, so then I do my job and have another question. So the term QKD is either, the D stands either for distribution or derivation, but it's, if I would play devil's advocate, it's a key agreement where both sides somehow by some quantum magic come to the same secret from which a key is derived, and it's not actually a key distributed. Is this correct? So you don't distribute the secret, you just agree on a secret.
Yeah, I guess it's terminology, but you can say that Alice distributes her random key to Bob, and then he decodes it, and then they agree upon what's the correct key, I'd say.
There's another question.
Hello, yes, I have a question. I'm not an expert, but I'm assuming that if you want to do that, especially with photons on a fiber, if you have a repeater in the middle, it's going to break, right?
Yes, so that's the biggest issue with QKD right now is that you have also a length requirement. You cannot. Right. You need repeaters for it to work. So you introduce like.
You break the tunnel.
Yeah. So you kind of break the security already there. So you need trusted repeaters, and again, this is only for research, but I think if somebody is afraid that their conversations are listened into, then right now QKD only supports distances where you could almost take your car and go directly to that person where you can have a meeting instead of doing it with QKD. But then again, all research starts at one place, and then we build it from there.
Okay.
Yeah.
Thank you.
All right. Calling once, calling twice. All right, then let's thank the speaker once more.
Thank you.